So ji, welcome back. This will be the second lecture about toric varieties. So let me just recall some things and then fix some terminologies, because there is something called normal varieties, or we call so if we are talking about affine varieties, then normal affine varieties. So there is something called a normal ring, and it works in the following way: that let R be an integral domain and K be its field of fractions. So whenever we have an integral domain, we can always create the corresponding field of fractions. So let us consider that field of fraction. We say that R is normal, or it is also called something called integrably closed if for any alpha in K such that there is a some monic polynomial in R of x with alpha its roots, implies that this alpha actually belongs to R. Okay. So such rings are called normal rings, okay, or integrably closed rings. So the thing is that if we start with an irreducible, so let V be an irreducible affine variety, okay, then of course it means that the ideal corresponding to this variety is prime, and this in principle means that the coordinate ring corresponding to this variety is an integral domain. Okay. So if the coordinate ring of corresponding to this irreducible affine variety is normal, we say that the variety itself is normal. Okay. And it's just that the normal varieties are kind of easier to handle. They are nicer objects in the area of algebraic geometry. They behave very well when people start studying about divisors and the extensions of regular functions and creating the birationality when they are resolving a singularity. So that's why we always start with normal varieties. And the good thing is that if we start with a non-normal variety, so a variety which is not normal, is very easy to actually create a normalization of that variety. Okay. So that's why the thing is that even if we start with a non-normal variety, we can normalize it, and the normalization is very simple. You simply define something called the completion of this variety. So a normal completion, so let's say it's kind of like CV, and that is you take all alpha belongs to the field of fractions such that alpha is integral over our C of v. What does it mean? It means that alpha is the root of some monic polynomial. Okay. And then you can create this this extension, and then this extension is a finitely generated algebra again, and this will give you a normalized variety corresponding to variety v.
Can I ask what's kind of the simplest example of an integral domain which is abnormal?
Which is not normal. Oh, okay. So let's consider this one. Simplest one is actually x square y cube. Okay. So that's like or how you should say. So the variety, rather than writing in this way, that's wrong. The coordinate ring of V associated with the variety V, which is the variety of x square minus y cube. Okay. And by the way, that's the reason why I'm gonna focus on these ones is that this normality actually gets associated very easily with something called strongly convex property of a polyhedral cone. Okay. So for us, looking that some variety is normal or not, it's actually very easy. We just have to see that the corresponding cone is strongly convex or not. Okay. So for example, I can show in a moment that the cone corresponding to this variety is not going to be normal, strongly convex. Okay. So by the way, in algebras there is another example where you can actually see what is going on. So because what we want to see that there is some root in my free field of fractions which is not an element here, right? So let's say you take this algebra for example, and T cube and T4. Okay. So this is an algebra, and note that what is going to happen is that there is this element S4 T4, okay, which correspond to the lattice point 4, 4, okay, and 4, 4 lattice point can be written as 2, 2. So there is another element S2 T2. Okay. And this S2 T2 is the root of the monic polynomial, which is x square minus x4 T4. Okay. And the problem is that this element, you can very easily see here, cannot be written, cannot be here in this thing. Okay. So then this coordinate ring is not normal. Okay. On the other hand, if you put S2 T2 here, this was one of the actually examples where I was defining this rational cone. Okay. So then it becomes normal. Okay. So in other words, the normalization of my variety before was actually this one. Okay. I only have to plug in this root which is not there. Okay. So the thing is that again, because what we can do, we can always normalize varieties, and the good thing about the normal varieties, why we want to actually study these varieties, that they are something very close to something called the smooth varieties. Okay. So there's a result which says that every irreducible smooth variety is actually normal. Okay. So the converse of course is not true. For example, in this example as well, this variety, the coordinate ring corresponding to this variety is not normal, not smooth, there is a singularity at the origin 0, but nevertheless the variety itself is normal. Okay. So, these normal varieties are like very close to being smooth. Okay. And so the idea is that in the end we have a very nice how to say algorithm to smoothen out a variety, a toric variety, and it works very well if we start with the normal variety. So, if we take a cone corresponding to a normal variety, we can smoothen out that normal variety in some way, and we will get something which is now smooth. Okay. So, now for us recall that for us when I say an affine toric variety, this comes from a spectrum of some semi-group of algebra S sigma, where S sigma was sigma dual intersection with the character lattice M, where this M of course is the character lattice associated to the torus which is here as a dense open subset. Okay. So, we should fix some terminologies, because that is exactly how we see that looking at a cone we can very easily see that whether or not some variety is normal or smooth or these kind of things. So, there are some properties which we can associate with the cones. The first thing is that if we are given a cone, okay, and we creates this dual, then there is a very nice relation between these two things, and that is the following. So, let M1 up to Ms be the generators of the edges of sigma dual, then to each edge M I can associate a set Mi positive, and that would be all u belongs to the vector space Nr such that M comma u is greater than or equal to 0. Okay. So, these are called the sporting half spaces or closed spaces. So, the property they possess is the following, that the cone sigma is nothing but actually intersection of all these sporting half spaces. Okay. So, you can see it very easily in an example. So, let us say this is your cone. So, this is your sigma. So, this cone is generated by two vectors E1 plus E2 and E2. Okay. And now, the corresponding dual I can create in this way. So, the dual cone is this one. Okay. So, that is your sigma dual, and note that if I take M to be 1 comma 0, okay, then H M positive would be all u belongs to Nr such that M comma u is greater than or equal to 0, but that would mean all u belongs to Nr such that u1 is greater than or equal to 0, right. So, if I want to like draw this thing here, so u1 greater than or equal to 0 would mean hold this portion. Okay. And now if I take m prime to be minus 1 comma 1, that will give me another hyperplane m prime, which is going to be u belongs to n r such that minus u1. So, u2 is greater than or equal to u1. Okay. So, that is you have this line and everything which is here. Okay. And note that this cone sigma is actually in fact m positive intersection with m positive. Okay. So, in order to recover the data of sigma out of if you are given a sigma dual, okay, you can recover it from in this way. Okay, that what region is going to represent your sigma. And the second thing is that we would like to so that would 4. So we would also like to define something called the relative interior of a cone. Okay, and this is all u belongs to a cone such that m comma u is greater than strictly greater than 0 for all m belongs to sigma dual subtract something called sigma orthogonal, where this sigma orthogonal is this set that this is all m belongs to m r such that m comma u is equals to 0 for all u belongs to rather than m r. So, u belongs to sigma. Okay. So, in other words, this actually going to be precisely represent if you have this cone. So, this precisely going to represent every point which is here in the interior. Okay. So accept the edges. Okay. And the thing is that if you have two, so why we need it? If we need it because of this thing called separation lemma. Because what actually we are going to do now, we are moving towards something like, I don't want to always restrict myself towards affine toric varieties. I want to glue these toric varieties somehow, affine pieces, to create an abstract variety. And one key ingredient would be understanding what happens if you have two cones which have this common face. Okay. So the thing is that if you have two cones sigma 1 and sigma 2 be two cones, okay, in your NR such that there is a common phase tau between sigma 1 and sigma 2, okay, then the common phase tau can be realized as HM intersection with sigma 1, and this also can be realized at HM intersection with sigma 2, where HM is actually all those u belongs to NR. So, NR such that M comma U is equals to 0. Okay. So, in other words, I can take this tau to be this, where this M which I am taking is actually belongs to relative interior of my cone sigma 1 dual intersection with minus sigma 2 dual. Okay. So, this lemma is called separation lemma, and this is actually a very basic lemma in the theory of rational polyhedral cones. Okay. So, that if you have a common phase, that common phase can be realized in this way. Geometrically speaking, so what does it mean is the following. So, note that if you have this cone and you have this cone, so let us say this is your sigma 1, this is your sigma 2. Okay. So, these are the two cones, then I can create the corresponding duals. The sigma 1 dual is going to be, so
What exactly is it requiring at the intersect along the face? Because generally the intersection will be another cone.
yes.
So,
Yes.
well, it does not, it will be of the same dimension.
Of the
They will not intersect, normally two cones will have a bigger intersection than just like a common face.
what do you mean they have the bigger? Oh, I am talking about when I have a common face among two cones.
So what's the thing that's saying that the intersection should be a common face?
So, that's just, so let us say okay, so you are saying that there is something missing actually.
Yeah.
And you have a common phase tau, which is the phase of sigma 1 and tau phase of sigma 2.
Okay.
That is what you are saying. Okay. Sorry. So, okay. So, this is your sigma 1 dual. Okay. And now the sigma 2 dual would be what? Sigma 2 dual would be this. So, this and this. Okay. So, I am gonna let me just paint them. This would be sigma 1 dual and this would be sigma 2 dual. Okay. And now, what I want to do is I want to take the minus of sigma 2 dual. Okay. So, minus of sigma 2 dual is something this. Okay. Sigma minus of sigma 2 dual. Okay. So, this is the minus of sigma 2 dual, and you can see that both have what? Both have a m which is in which you can see as the on the boundary of this thing. So, okay. So, what you can do, you can realize you can take any m in the intersection of these two things, which is actually this phase. So, let us say m to be minus 1 comma 1. Okay. And then you can realize, note that the h m would be what? It would be all u such that u 1 is equals to u 2. Okay. And if you intersect this thing with sigma 1, you get actually tau, right, because that would be intersection of this thing, which is u 1 equals to u 2, u 1 equals to u 2 here would be this line. Okay. And its intersection with sigma 1 dual would give me this edge. in this direction. Okay. So that would be the common phase. Okay. So these are some terminologies which I wanted to fix, and now I can talk about so now I can talk about how normality is associated with cones. So I have to define a property. We say an affine a semigroup S inside a cone, inside a lattice, is saturated if for all k from the natural numbers minus 0 and m belongs to m, if we have this, that k m belongs to S, then m also belongs to S. Okay. So this is called a saturated group, and it turns out that saturated groups, semigroups, can be related with something called the affine semigroups coming from the strongly convex rational polyhedral cones. So what does it mean? It means that if you have a sigma, we say it is strongly convex, if and only if any one of the following happens, that 0 is a phase of sigma, okay, and sigma intersection with minus sigma is 0, okay, and that dimension of sigma dual is equals to n equals to the dimension of your vector space MR. And there is one more, which is that there is no proper positive subspace, positive dimensional vector subspace in this space. Okay. So one other result, which is it's not hard, but it's a little bit lengthier to show that but rather than that one. So the thing is this one: if S is saturated, then S actually is equals to S sigma for some sigma which is strongly convex rational polyhedral. Okay. And why this is important, that realizing that actually the saturated affine semigroups comes in this way, that is this proposition. Let C of V be a normal toric variety, so affine toric variety, so rather than doing let, if then C of V, so rather than spec of this C of V can be written as some C of S, where S is saturated. Okay. So, let me show you this very quickly, that this actually does happens. The thing is that this part is okay. If you have an affine toric variety, then that affine toric variety comes as a spec of some affine semigroup algebra.
Define the normal affine toric variety in a similar way.
Sorry?
You can define because there is a proper definition of a normal variety.
Uh-huh.
So you can define the normal affine toric variety in a similar way.
What do you mean by in a similar way?
There is a definition that the coordinate ring should be.
Yeah, so it should be normal.
So the same definition holds.
Yeah, sure. That's I think you joined little bit late, so that's where I started. Okay, so yeah, the thing is this one, that if you have a normal toric variety, okay, then that normal toric variety comes as all affine toric varieties comes as a affine semigroup algebra, right? Spec of some affine semigroup algebra, right? So for every toric variety, you can have some S, which is an affine semigroup, which is embedded in your lattice M. Okay. Now the thing is that if your toric variety is normal, okay, then this affine semigroup algebra is actually saturated. Okay. And actually the converse is also true, but the converse is a little bit like lengthier. So, I'm going to prove this first. Okay. So, let that your C of V is this C of S, and I want to prove that this S is saturated. Okay. So, that would mean, so let M belongs to your M and K belongs to 0, such that Km belongs to S. Okay. So we want to prove that if Km belongs to this S, then this M belongs to S. That is what we want to prove. Okay. Now the thing is that Km belongs to S means that this character Km, this element, this belongs to your C of V. Okay. So this belongs to your C of V. On the other hand, this character is a polynomial on your torus Tn. Okay, because characters are defined in this way. So if you have a polynomial on some affine open subset of a variety, you can say that that polynomial is a rational function on your variety V. Okay, because the way is that you take an affine open subset, and the coordinate ring associated to that affine open subset comes as the localization of some via some element F. Okay, and then the polynomials in the coordinate ring of this affine open subset are naturally, they are living in the rational field of fraction of your coordinate ring of V. So they are rational functions there. Okay. So what I mean by rational function, I mean that this element is the element M. So for example, K of M and also M belongs to the field of fraction, which I can represent in this way. Okay. So
as you mentioned earlier, that the coordinate ring of the normal variety is C algebra generated by an affine semigroup.
Yes, this was the whole fuss which we done in the last lecture.
Okay.
Yeah, that if we have an affine toric variety, it comes as the spec of the affine semi-algebra, semi-group algebra.
And what about in the case of normal varieties?
So it doesn't. Normality means that you are putting an extra condition on your toric variety. So if something is true for any affine toric variety, it means that it's true for the.
So this will also hold for affine toric varieties.
This is all. This only holds
for affine varieties.
Yeah. This is affine toric varieties. I'm talking about affine toric varieties. So this result is saying that if you have a normal and of course, the normal affine I should put irreducible, because otherwise C of V will not be an integral domain. So that would be a problem. So this is just saying that if you have a normal affine toric variety, the affine semi-group algebra which I associate affine semi-group which I can associate with that normal affine toric variety irreducible is actually saturated. Okay. And the fact is that since saturation comes from a strongly convex rational polyhedral cone, so it means that this in this language of algebraic and algebraic sense and in the cone sense, the normality associates to strongly convex rational polyhedral cones. Okay. So if we can prove this, then that's and that's done. I mean, I now know that my xm lies in the field of fractions, okay, and clearly this can be written as x power k minus km, okay. So this equals to 0. So this xm is the root of this thing, okay. So this would imply that the character m belongs to C of S. Why? Because C of S is normal. So if you have a point in the field of fraction which is a root of some monic polynomial, then that point should also should be in your ring C of S. So, but if this is in your C of S, that would mean that M should belong to S. Okay, because C of S, अगर आप लोग को याद हो, that was some C characters M where M belongs to S. Okay. So the thing is that if you have a normal irreducible variety, then it comes via a saturated affine semi-group, and that saturated affine semi-group can then be associated with a strongly convex rational polyhedral cone. So there is this correspondence, which is that in toric geometry, so in toric world, normal affine varieties means strongly convex rational polyhedral cones. Okay. So if you want to talk about normal varieties, you need to restrict yourself to this normal strongly convex rational polyhedral cones. Okay. So now the other fact which is actually more interesting is this following.
Okay, in the affine case, we can compute the normal closure by computing the integral closure of the coordinate.
Yeah.
So do we have a similar result here?
Yes, exactly. So what we need to do here is, if something is not normal, we should have to make it normal. Okay. So
you have to associate some cone
yes,
with the integral closure of C.
yes, okay. So we can do that. That's the idea, that if something is not normal, then we take its corresponding cone and look for where the normality fails, okay, add those minimum generators corresponding to those points, and then create a new cone, okay, affine semigroup that will be saturated. Okay. So, for example, in this case when I was saying that take this thing as 4, 0, 3, 1, 1, 3 and 0, 4, okay, then the group S which I can create from this is NA, okay, in our language. That's all the natural sums of linear sums of these points, okay, and this is clearly not saturated, okay, this one, because clearly here there is an element 4, 4 which is a 2 times 2, 2, but 2, 2 is not in this S, okay. So, what I have to do, I have to like simply create A tilde which is going to be 4, 0, 3, 1, 2, 2, 1, 3 and 0, 4, okay. So, the point which was missing I just added it there, okay. And now the S tilde which is N of A tilde is actually saturated, okay. So, in other words, the variety which corresponds to this affine semigroup associated to this affine semigroup and the variety which is associated to this affine semigroup, they have a relation that this is the normalization of this variety, okay. So, that would be the way to do normalizations. Okay.
And the integral closure of CV is equal to the
S tilde, yeah, exactly, okay. So, also integral closures means that what is going on? Normalization means that if you have a point in your field of fraction which is a root of some monic polynomial over the single variable polynomial ring of polynomials of your R, then that point alpha should be in your ring itself R, okay. So, that means that alpha is an integrally closed point, an integral point probably, I think the proper definition would be, so integral point in R, okay. But the thing is that now it means that what we are missing, if something we want something to be normal, which means integrally closed, that any time when you have an monic polynomial which is a root, which gives me alpha as a root of that polymonic polynomial, then alpha belongs to R. So, the missing point are precisely those alphas which does not satisfy, they are root of monic polynomial, but they are not inside your ring R. So, you simply add them. It's integral, it's called.
The back closure is the definition for fields.
Yeah, so it's the rings.
We have a similar kind of.
Yeah, so it's integral closures, some kind of thing. Okay, so you can always create this. I mean, I think so. There's a software you got normalizer something. So you can actually, if you give me a ring, there's actually a program. So you put that. So they give you there are algorithms to give you the normalizations. So that's why the thing is, that's why in modern algebraic geometry people don't like spend more time on non-normal varieties. They say, okay, you have a non-normal variety, you can always normalize it, and then you can look for the normal varieties, okay, and normal varieties are nicer to deal. So why not we just fix ourselves to the normal varieties.
But is it like integrally closed means that the integral domain contains its ring of algebraic integers, like monic polynomial?
Not necessarily.
No.
For example, if you will take, for example, in the case of field, we know that C is an algebraically closed field.
Yeah.
But whenever you will take the integral closure of Q, so you will not get C.
Yeah.
So algebraic closure of Q is not equal to C.
Yeah, but but so I can define, I guess. So there is ring of. So the only difference is basically you want monic polynomials with coefficients
in your ring. In your ring, yeah, yeah, in your ring,
yes.
yeah. Okay, so so that thing is that now we will always restrict ourselves to the strongly convex rational polyhedral cones. Okay, number one. Number two, we can say something about that. We say sigma is smooth, and I'm not going to spend now most time. I'm going to say that smoothness means that it relates to when variety is smooth. So sigma is smooth if that the edges, the ray generators so minimal ray generators of the edges of sigma form are part of a basis for Zn. Okay. So what does it mean? It means that if you have, let's say, this cone generated by 1, 1 and 0, 1, okay, the ray generators are actually 1, 1 and 0, 1 of the edges. Okay. And note that these two generators are also the generators of your Z square. Okay. So you can actually very easily realize that. By the way, if you want to see that if someone is the basis, if you have like n vectors and you want to see if they are basis of Zn, all you have to do is take the determinant of this thing, and if determinant is plus minus 1, then you are done. Okay, otherwise no. Okay. So in general, a cone can be a strictly less dimensional cone as well. So then it means the part means that if you take the edges of ray generators of the edges of that cone, then that set can be extended to become a basis of Zn. Okay. So that is what when I say. But for a maximum dimensional cone, this precisely means that if you take this matrix, the determinant of this matrix should be 1 and minus 1 or minus 1. Okay. So and the thing is that we say V is smooth if and only if the corresponding sigma is smooth. So I should like I'm not going to spend time now on this one. This is actually a very nice proof to show that this is actually smooth if this happens. But I want to move towards away from this affine toric varieties and towards abstract varieties. So I really would like to say something about those things. First thing is that there is a notion of projective toric varieties. And again, the reasons are again the same. So the thing is that every affine variety can be realized as a sub-variety in some projective variety. All you have to do is you take the ideal, the generators of the ideal corresponding to the affine variety V, and you homogenize those generators, okay, and then you will have an ideal which is an ideal generated by homogeneous polynomials, and you take the variety corresponding to those homogeneous polynomials. That by definition is the projective variety. and then all you have to do, your variety of affine variety is simply equals to the to homogenize, you have to introduce one extra variable. So your affine variety is simply saying that that extra variable put equals to 1. Okay, so that will become your affine variety. So the thing is that if you have an have a affine variety, you can homogenize it and you can realize it as a subvariety in something called the projective varieties. Okay, and the good thing about projective varieties here is that, like Cn, recall the Cn was a affine toric variety, right? So it has a torus. Similarly, this space Pn is a toric variety. Okay, and we have to realize this. Okay, so what we need to do, we need to put establish a cone corresponding to this. Okay, that cone should be something which is again is isomorphic to Pn minus this variety, homogeneous variety, x naught product xn. Okay, so you take the Pn variety and you subtract from it this homogeneous part. Okay, and the thing is that this actually means that all points T naught up to Tn in your projective variety Pn such that that Ti belongs to C star. Okay, and then the property of the projective spaces is that these are the classes, and you can realize it as, if you multiply with T naught inverse, then you can realize this thing as 1 comma some T1 up to Tn sub in Pn, where these Ti's are again in C star, and this is the something associated at C star. Okay, but there is so we have a torus, that's okay, that's not a problem. It's clearly a dense open subset because it's an open subset coming out of subtracting or what you can say that the solution of one function. So the thing is that what would be the corresponding lattices which we can associate with these toric variety, these toruses, and that's a little bit different than what we were doing previously. Note that if I want to create a character from this Tpn to C star, okay, I can do that by doing the following. I can take a character, a element from here, C star n plus 1, okay, to C star. Okay, and how I do that? I say that that's equal. That is, I know that comes via a vector in Zn plus 1, right? So what I do, I say that m applied on T naught up to Tn, and then I can make a projection here, natural one. So I can do this, I can apply this projection on this one, and I consider it as T naught A naught up to T1 A1 times Tn An, and the other way around. So projection here and then applied on this one. Okay, so first the projection, and then if I applied this thing, so that would be T naught A1 times Tn An. Okay, so what I'm saying is that take an element here, okay, take its corresponding element here, which is simply the T naught up to Tn, and apply this character in such way as this is the character this one. Okay. But the only thing which I have to be very, very careful is what? Is the following, that if I apply this character on lambda times T naught up to Tn, okay, this should also be equal to this thing, right? But this would mean that lambda power A naught plus An T naught A naught times Tn An should be equal to this thing, okay. But that would implies that A naught plus An should be equal to 0, okay. So I have to put a condition on these m tuples, which these vectors m's which I'm taking, m which I'm taking in Zn plus 1, okay, and that condition is this one, okay. So that would mean that the corresponding character group, let's call it Mn, is all A naught up to An in Zn plus 1 such that A naught plus A1 plus An is equal to 0, okay. And then if I want to define my n, the dual lattice to M, that would mean that I want a C star from here to Tpn, okay. And that again I can create corresponding to a C star from here to C star of n plus 1 a lambda u. So what I do is I take a T and I send it to T power B naught up to T power Bn, okay. So I can send it here. Then the thing is that something is going to happen. If I apply on this the character gamma m which goes into C star, so now I apply the character here, that would be equals to T power B naught A naught plus up to so and so on A n B n, okay. So that is a character from C star to C star, okay. And now note that these A naught and A n has this condition that A naught plus A n should be equals to 0, okay. So in other words, if I choose B naught up to B n to be 1, 1, 1 or any multiple of this thing, okay, in that case this will become a T power k times A naught plus A n, okay. But this A naught plus A n is equals to 0, so that would mean that this will become 1, okay. So in other words, the character associated to the C star is actually constant character and it goes to 1, okay. So that would mean that all these elements will create an identity composition, right. So that would mean what I need to do is I need to take this Zn plus 1 and I quotient it with 1, okay. So there are two relations on so there is a relation on the character lattice which says that A naught plus A n should be 0, and there is a relation on the other lattice, okay. So that should be satisfied. So any question? हाँ जी, कुछ समझ नहीं ना आ रहा, नींद आ रही, so Hanji. So the point is, I have yet another way of realizing projective spaces, for example, and the way we realize it, if someone has done that in differential geometry or somewhere else, that they realized a projective space as gluing of some copies of Cn. Okay? And it turns out that that same gluing I can recover from some data, some toric data. Okay? So, for example, let me fix myself to the projective space P2. Okay? In P2, I can associate sets like U naught, which is 1 comma, so this x naught, x1, x2, such that x naught is not equal to 0. Okay? And then I can have U1, which is x naught, x1, x2, such that x1 is not equal to 0. And then I have U2, which is x naught, x1, x2, such that x2 is not equal to 0. Okay. Now, these things can be realized as the spec of C of x1 over x naught and x2 over x naught as a algebra. Okay. This can be realized as spec of C of x naught over x1 and x2 over x1. Okay. And this can be realized as spec of x naught over x2, x1 over x2. Okay. Now, note that what happens when I say that I am in the intersection of any of these. Okay. So, let us say you take the intersection of U naught and U1. Okay. So, if I want to see this intersection U naught intersection with U1 inside my U naught, okay, then this is an affine toric variety, and associated to this affine variety, this is a subvariety. Okay. And that subvariety comes from this spec of C of x1 over x naught, x2 over x naught. Note that when I say that something is in U naught and U1, it means that x naught is not equals to 0, x1 is not equals to 0. So, in other words, x1 over x naught is invertible. Okay. So, that is exactly I would do. Okay. So, I would take the localization of this algebra on this one. Okay. And if I see this U naught intersection U1 as something in U1, okay, that would mean that I can realize that spec of C of x naught over x1 and x2 over x1 localized at x naught over x1. Okay. So, I can see that. Okay. And now, recall that there was this gluing data. So, what you can do, you can construct a morphism from you can construct a morphism G, let us call it 1 0 from U naught intersection U1, where I am realizing this one as a subset of U naught to u naught intersection u1, where I am now realizing this one as a subset of u1. Okay. And that is simply goes in the following way, that the element x naught over x1 goes to x1 over x naught, or and the element x2 over x naught goes to the element x2 over x naught divided by x1 over x naught. Okay. If I am not wrong, yeah. Okay. So that would be the gluing data. So that's why, that's how I can translate from in the intersection, from realizing the points in the intersection as points in u naught to realizing those as points in u1. Okay. So this process of us being able to do that is called associating a data which is called the transition functions, or together if we have recover all the transition functions, we call them the gluing data. Okay. And they have to satisfy some properties, but note that this thing, if I want to do this algebraically, that would mean what? I have two affine varieties, and the gluing data is, or this transition function is nothing but a morphism between these affine varieties. Okay. So that would mean that it should come from some C algebra homomorphisms. And if these intersections, because these are really the intersections, so I want them to be isomorphisms, not just morphisms, then in C algebras they should come as isomorphisms. Okay. And note that I can realize in the following way, that G10 dual should be a map from x1 to x2 over x naught, x1 over x naught. Okay. And what should happen, that the inverse is, note that if I take this x naught comma x1 which I am inverting, its inverse is actually x1 over x naught, on which I am taking this localization. Okay. And then if I take this x naught over x1, this in this algebra I can realize as what? Yeah, x naught over x1 I can realize as x naught over, so I want to realize it in this way. ये सही में जा रहा हूँ? हाँ, I mean, yeah, I mean the thing is that it's actually x naught over x1, but I want to see it in a different way. I want to see it, yeah. So I want to see it as this thing, that x2 over x naught. Okay. So how should I do that? I mean, oh, sorry. What I'm doing is wrong. Yeah. Yeah. That's what. मैं भी कह रहा हूँ हुआ कि ये बन ही नहीं रहा. x2 over x1 can be realized as x2 over x naught divided by x1 over x naught. Okay. So this is the exactly the identification. Okay. And note that actually we can see in a similar way we can try to build an identification from here to here, and if you do that they are inverse of each other. So if you compose them together you get the inverse of each other of both. So that's the definition of the transition function should have an inverse, and that inverse should be coming this way. And then again, and the other thing in the transition functions is that what happens if you have three open subsets and something is in the intersection of all those three. Okay. So that is called something called the cyclic property. So the cyclic property of the transition function should be this one. So that is another requirement which should be there. So if you want some alpha gamma, that should be equals to some alpha beta compose beta gamma. Okay. So if you have you are in the intersection of three sets, then this should hold. Okay. So this is called the cyclic property. Okay. Okay. And the thing is that if you have affine varieties and you associate with any set of affine varieties this gluing data, that on the intersections you have this transition functions with their inverses, and on the triple intersection you have this cyclic property, then that's exactly how you can create something called an abstract variety. Okay. So an abstract variety is a variety which locally kind of look like affine. Okay. And on the boundary, on the intersections, it translates via these transition functions. Okay. And the thing is that for Pn, P2, I'm going to give you a data, and time क्या हो गया? Huh? So let's say you have this cone, and this cone, where this cone is 1, 0, 0, 1, okay, and this one is -1, -1. Okay. So these are three cones, sigma 1, sigma 2, and sigma 3. Okay. And all these three cones separately will give you something called the affine toric varieties, right? Number one. Number two, you can very easily check now here that whatever the corresponding affine toric varieties are going to be, they are smooth. For example, this 1, 0, 0, 1 forms the basis of Z2. 0, 1, -1, -1 forms the basis. -1, -1, and 1, 2, 0 is also forms the basis. So these all are smooth toric varieties, and the dimension of these toric varieties, because the dimension of corresponding sigmas and sigma duals is 2, so the dimension of corresponding affine pieces are 2. So what we have essentially is we have 3 copies of C2. Okay. And the corresponding algebras are actually Cx, y, corresponding to this one. Corresponding to this one is C of x inverse y. Okay. And corresponding to this one is C of y inverse x y inverse. Okay. These are the corresponding algebras. And if I do a little bit trick that I say x goes to x1 over x naught and y goes to x2 over x naught, okay, you can actually see that these affine pieces are exactly these algebras. Okay. That would be the first thing you should realize. Number two, the important thing, that's why we were actually talking about that relative interior, was this one, is this one. If you take this cone and this cone, it has a common face. Okay. Now this common face is going to be realized as some HM intersection with sigma 1 and HM intersection with sigma 2, where AM जो है वो आपके पास जो है relative interior of sigma 1 intersection with sigma minus sigma 2 dual के अंदर है, right? And if you do that, in this case, that M you can take as, let's say, 1, 0. Okay. Then the properties which I think, so what is going to happen is the following. that if I want to realize this u sigma naught or sigma 1 intersection with u sigma 2, okay, this is going to be spectrum of C of S tau, the corresponding intersecting phase, okay, or this is equals to spectrum of C of if I am talking about I am realizing this inside of sigma 1, then this is going to be sigma 1 localized at the character associated with M, where this M was in the relative interior of that thing. Okay. So, that would mean in our case for C of x comma y, इसके लिए that is localization on x. Okay. And note that even this thing which creates the localization, and then of course you can realize this thing as subset in u of sigma 2 as well, and there the localization would be x inverse y localized at x inverse. Okay. And note that if I replace x with x1 over x naught, then this is exactly the localization of u naught intersection u1 realized that in u naught. Okay. And if I do this one, that is realizing that intersection in u1. Okay. And it turns out that exactly the corresponding data which I can get, the gluing data which I can get is exactly that which I can get from there. Okay. So, in other words, if I have affine cones, collection of affine cones in a well suited way, arranged in a well suited way, then I can construct abstract varieties by recovering all the gluing data from my from my that nice data. That nice data is called something called fan associated to the abstract varieties. So, what do you have is the following, you need to make it nicer. So, you like जब जैसे अजीम ने कहा तो that intersection जो है दो varieties दो cones की need not to be intersecting on the faces, right. So, so we have to refine everything so that we always get that thing. Okay. So, in that case that is called a fan, and it has a property that you have all these strongly convex rational polyhedral cones, and then every two strongly convex rational polyhedral cones has this property that their intersection is again a strongly convex rational polyhedral cone that is inside there in that set, in that data. And then for every cone their faces are also there in that data. This is called a fan. Okay. Satisfying all these properties is called a fan. And if you have a fan, you recover something, an abstract toric variety which is normal, because it's normal because every affine piece is normal, because the cones are strongly convex. Okay. So, every affine piece is normal. So, the abstract variety is normal, and the gluing data you can always recover by doing this, that that you have this, and then you have spec of C of some u sigma 2 intersected at minus m. Okay. So, if you have the common face, okay, then you can do in this way, and that will create the map. Okay. And that will create the gluing. Okay. So, all you have to do, you have to realize that these things are isomorphic to each other. So, you have to develop those maps as C algebras, and then their corresponding induced maps on varieties are the gluing data. Okay. And then we can deal with something called the abstract toric varieties. So, I should stop here, I think so. तो बड़ी खुश हुई हैं हैं